Hello everyone. Let's continue our discussion of frequency response analysis. Um, let's see. Last time, right before we stopped, I wanted to do an example of getting a transfer function, solving for a transfer function for a circuit, right? And typically transfer functions are things that relate some output in the circuit to some input. The output could be a voltage or a current, and the input could be a voltage or a current, right? But it typically is it is a representation of the ratio of a certain output divided by a certain input. So it kind of gives you an indication of what would the output be if you have a certain input. Okay, that's why it's called a transfer function. So let's do this example. So the example is the following circuit. So I have some input, and again, it's not a fixed frequency. I can sweep the voltage. Sweep the frequency. When I'm sweeping the frequency, I will tend to not do this arrow. It's understood that this is a phasor, right? In this case. And then I have R1. I have an inductor. It has an impedance of SL. Remember, S is just a neat way of writing J omega. Shortcut for writing J omega for now. Right? That's how we will think of it, and that's how you should think of it. Right? And then I have a capacitor with an impedance of 1 over SC. Then I have a resistance R2. Right? And then we have a voltage V2S here. So, and then I have the mesh currents I1, S, and then I2, S. We want to find two transfer functions. We want to find I2S over V1S, and then we want to find V2S over V1S. All right. The first step, of course, is writing the mesh equations. So let's start with mesh 1. So I have on the other side V1S. I just take it directly to the other side, and then I move clockwise along the mesh. So I end up with R1 plus SL I1. So this is the I1 component. It sees impedances R1 and SL. But then there's the minus I2 component that is going this way, right? So this is going to be minus SL I2 S, and I said I don't want to do the arrows, right? So this is equation 1. Now we go to the second mesh, right? And then before we do the loop, let's do the component from this mesh. So this is a minus I1 times SL. So that's first component of the equation will be minus SL I1 S, and then we'll go through the loop. So we're going to have the total impedance, which is SL plus 1 over SC plus R2. So I'm going to have SL plus 1 over SC plus R2, all of this times I2. S gives me 0. This is equation number 2. Equation number 1 and equation number 2. And to solve, we need to solve for I2 to get the transfer function, right? If we solve for I2, we can just divide it by V1 and get the transfer function. All we have to do is now just manipulate those equations. And there are many ways to solve this. You could go to MATLAB and use a symbolic toolbox and write two equations as matrices and try to use the symbolic toolbox to get a symbolic answer, or Mathematica, or you could just, do substitution. It's a little bit cumbersome, especially when you're doing it symbolically, but it works. So my strategy here is going to be to write I1, use equation 2 to write I1 in terms of I2, and then sub that I1 into equation 1, right? And that allows me to get a solution for I2. So what would I1 be? Let me take I1 to the other side. I'm going to have I1 S. I'm going to divide by SL, so I end up with SL plus 1 over SC plus R2 I2S over SL. I just rearranged equation 2. That's all what I've done. And then let me simplify this further. Let me say I1s equals, let me place the SL inside the bracket. So I end up with 1 plus 1 over S squared LC plus R2 over SL, I2S. Right? And then I take this equation and I sub in equation 1. What happens when I do that? This is equation 1. So yeah, and I'm going to have R1 plus SL. And then instead of I1, I'm going to substitute this. So I'm going to end up with 1 plus 1 over S squared LC plus R2 over SL, I2 S, and then the rest of the equation is minus SLI2 minus SLI2 S equals V1S. I can take I2S as a common factor and then divide both sides by the term, by the remainder after I take I2 as a common factor. So I took I2S as a common factor, and then whatever I took I2 from, I divide by that, and I move it to the other side. So I end up with V1S over R1 plus SL, and I'm just writing things down now, times 1 plus 1 over S squared LC plus R2 over SL. Right, this is the first term, and then I have minus SL. Remember, I took I2 out, so I have this term minus this term. Okay, and then this is my transfer function. I just can move V1 to the other side, so I have I2S over V1S. And let me simplify a bit. Let me multiply both the numerator and the denominator by SL. So I end up with SL over R1 plus SL. And then I move in the SL into the second bracket. So I end up with SL plus 1 over SC plus R2 minus S squared L squared. And actually, let me do another simplification. Let me multiply the numerator and the denominator by SC. So I end up with S squared LC. And again, I want to multiply the SC to the second bracket here in the first term. So I end up with R1 plus SL times S squared LC plus 1 plus R2 SC. This simplifies things a bit. I don't have fractions anymore here. I would always like to reduce everything to a polynomial, of course, minus S cubed L squared C. Okay, so this is something that you should tell yourself once you see this. Is this going to be a cubed function of S? You should know that it shouldn't be. Why? Because this is a circuit that has two energy storage elements. It has only a inductance and a capacitor. So this is a second order circuit. Typically you will find out that in a second order circuit, whatever transfer function you write will have nothing more than S squared in it. What will happen is that this S cubed will probably be cancelled out by something else in the expression. And we will find that out. We will discover that that's true. Right, let me continue the manipulation. So I have I2S over V1S equals S squared LC, and let me do what? Let me I guess multiply those two brackets. So I end up with S squared LC R1 plus R1 plus R1 R2 SC. All I did is multiply R1 in and then multiply SL in. So I get plus S cubed L squared C plus SL plus R2 S squared LC minus S cubed LC minus S cubed L squared C. Notice this cancels with this. S cubed L squared C cancels. So let's collect the terms. So this is a polynomial, right? So it's best to collect the terms in power of S. So I have S squared. What term do I have for S squared? I have LCR1, and what other S squared I have? Okay, I have LCR1 and I have LCR2. So I can take LC out, so I have LCR1 plus R2. So that's the S squared term. What about the S term? Well, S, I have here R1, R2, S. What else? And I have SL, right? So I have R1, R2C and L. So I have a term that is coefficient that's RL plus R1, R2C. So I covered that. And then finally, the coefficient of S to the power 0, which is R1, just simply R1. And then I have S squared LC. So this is I2S over V1S. And this is it. This is the transfer function. How do I get V2S over V1S? Just multiply both sides by R2, right? Because I2 times R2 gives me V2, right? So just multiply both sides by R2. So I end up with, instead of I2, I end up with V2, and then I have S squared LCR2. And then the denominator repeats itself. This is another common fact that you will see, that you will discover, is that when you do the transfer functions for different circuits, when you do for the same circuit, when you do a different transfer function, you might get a different numerator, but typically for the same circuit, you will tend to get the same denominator. The denominator is a bit kind of like a characteristic of the circuit. Remember when we talked about the characteristic equation? So this actually beautifully ties in with those polynomials that appear in the denominator. Okay. We will discuss that further later in the course, but keep that in mind. Okay, the denominator is the same, LC R1 plus R2 S squared plus L plus R1 R2 C S plus R1. And this is the other transfer function. Okay. All right. So we said transfer functions, whatever circuit you're dealing with and you're working on getting transfer functions will always tend to reach a form of a polynomial. After you do all the manipulations, they will reach a form of a polynomial over a polynomial. Something like this. So it's going to be like a general, most general kind of polynomial over polynomial will look like this. It's going to be like am s to the power m plus I don't know, am minus 1 s to the power m minus 1 all the way to a0 over an sn plus an minus 1 sn minus 1 all the way to, oh, let me call this b instead of a, so that's not confusing, all the way to b0. Okay? So there's something called the fundamental theorem of algebra. Fundamental theorem of algebra, which states that any nth order polynomial is going to have n roots. Any nth order polynomial is going to have n roots. Now those roots might not all be real. Some of those roots might be complex, right? But the theorem states that any nth order polynomial is going to have n roots, right? A second order equation is going to have, polynomial is going to have 2 roots always. Sometimes those roots might not be real, but they might be complex conjugate, but they'll always have roots, right? And furthermore, another statement I could make is that if the coefficients of the transfer function or of the polynomials are real, then any complex roots will always appear in complex conjugate pairs. That will always happen because that's the only way you can get real coefficients from the roots. If you have complex roots that do not come in pairs that are complex conjugates, then you will never get real coefficients, right? And when we deal with circuits, circuits always have resistances, inductances, and capacitances that are real, right? Voltages and currents that are real, right? So we can never, in the transfer function, we can never have complex coefficients. So the roots will always have to be either real or complex conjugate pairs, right? It doesn't make sense to talk about a 5J resistance. It does make sense to talk about a 5J impedance, but not a 5J resistance. Okay. So what's the point here? The point here is that because we can get roots for any polynomial, we can rewrite the transfer function in terms of its roots. So we can write the numerator as some constant, and then s minus z1, where z1 up to zn are the roots of the numerator, and then p1 up to pn, this is m, are the roots of the denominator. So knowing the roots, we can always write any polynomial using its roots. So we know that from basic math. So we can write the polynomial as s minus z1, s minus z2, all to s minus zm. Let's just multiply those terms together. And this is a polynomial, right? It's a first order equation multiplied by other first order equations m times. So we will get, if we multiply everything together, we will get an mth order polynomial. Furthermore, if s is equal to any of those roots, the thing will be zero, right? Because one of those will be zero is enough for the whole thing to be zero. Then the denominator can be written as s minus p1 s minus p2, and this constant captures any constants that could appear in the equation, meaning if s there might be some extra gain in the equations that we capture using this k. We could have some factor that we can factor out from the numerator, for example. So yeah, so s minus p2 all the way to s minus p. Now those z's are called the zi's are called the zeros of transfer function TF, and pi's are called the poles of transfer function. And the reason, of course, they are called zeros is obvious. When s equals any of those zi's, the transfer function will be zero. When s equals any of the pi's, the transfer function will be infinite. So it's kind of like those zeros, transfer function is zero, and those make the transfer function infinite. So having an infinite value at a certain point is like a pole. You can imagine it to be some pole, some infinite pole. So that's kind of like the traditional, historically, that's how the name that people settled on. I mean, there's no terrible deep meaning for calling those poles. That's just what people settled on. And you will hear a lot of that terminology, the zero poles of the system, when you study control theory. Okay. So so those are the zeros and the poles. Yeah. So it is one thing to have the transfer function, right, which gives us complete information, of course, about the frequency response, right? But I mean, it would be more convenient if we can like plot the frequency response graphically, right? So that we can observe just by eyeballing the response how the system reacts to different frequencies, and the transfer function does include that information, right? We said it's S just j omega, right? So really at every point in frequency we get hj omega, which is a complex number. So it is a complex number that has a magnitude and a phase, right? That's what a complex number is. And furthermore, this complex number varies depending on the frequency. Every different frequency will give me a different value for hj omega. And so the magnitude is going to be depending on omega, and the phase is going to be depending on omega, right? So, and that's what we said when we started talking about the frequency response. We said to describe the frequency response completely, because the frequency response is a complex number, we need to plot two things as functions of omega. We need to plot the magnitude, and we need to plot the phase, right? Now, we said that all transfer functions, whatever they are, when we're dealing with circuits or really any linear system, so circuits are linear systems, right? So when dealing with circuits or any linear system, all transfer functions tend to end up looking like this. So they will look like a constant, and then a bunch of zeros and poles. It's a numerator over a denominator, and we said we can represent the numerator as a bunch of zeros, Zm, over a bunch of poles, S minus P1, S minus P2, all the way to Pn, right? So we want to, and S is just j omega, right? So we want to plot this frequency response, and we could, always use a computer. Historically, that wasn't readily available. I mean, but we could, this day and age, use a computer and plug in different frequencies, get different values here, right? So this is the magnitude and this is the phase. The magnitude is just hj omega magnitude, and the phase is the phase of hj omega. So we could, for different frequencies, at certain frequency, plot the magnitude and the phase. Another frequency, right? So we can create a plot, that's fine. But it is helpful to, if there is a way we could rapidly sketch the frequency response and understand how it looks like, and get a decent approximation of it without having to write a program and plot it point by point. Turns out there is a way to do that, and that way of doing that, of sketching the frequency response, exists. That way is called the Bode plot. It's named after an engineer called Bode. I think he worked for Bell Labs. And this was all developed, I think, in the 40s, perhaps. Yeah. So how can we do that? How can we figure out how to kind of sketch the frequency response easily from the transfer function? Right? The key thing that we have to understand here is that we want to simplify the problem, meaning we don't want to think about how to plot this complex transfer function all at once. We can kind of divide and conquer. We can try to think, okay, how do I plot this pole by itself? How do I plot this zero by itself? How do I plot this gain by itself? So if I know how to plot each one of those by themselves, I can somehow then add them all together to get the resultant plot. This is the key element that allows us to build the Bode plot. Now the problem here is, because all the poles are zeros and multiplied with each other and divided by each, it's division and multiplication, we cannot just simply plot it plot each pole and zero separately and just add them together. That wouldn't work because they are multiplied together. Well, it will work if we instead take the logarithm of the whole thing. So instead of worrying about plotting hj omega, so instead of h, I'm gonna put j omega. Instead of worrying about plotting hj omega, which has a bunch of things multiplied together, right? I can instead plot 20 log hj omega, right? Why the 20? That's just a matter of convention. This by the way is called dB. When you take some signal and you take its log and multiply it by 20, you end up with dB. So if the signal is volt, let's say volt over volt, you end up with volt over volt dB after you take, or called decibels, right? After you take the 20 log. Right? So this constant doesn't matter much. It's just a matter of convention. It has historical reasons for it to arise. Right? It has to do mostly with power because dB actually is defined for a signal to be 10 log, right? But because sorry, dB for power, dB is actually a unit that has to do with power. So it's defined for power signals to be 10 log the power. But because power in electrical circuits is V squared, is proportional to V squared over, let's say, R, the squared can be taken out of the log. And this is what gives the 20. Right? So all signals in electrical circuits, to get to the dB formalism, we just multiply by 20 log. We find the log and then multiply by 20. Whatever the reasoning is, the key thing here is that it's the log function that simplifies things. 20 doesn't do anything, it's just a constant that is there for a historical reason. What the log does when I take the log of this expression, I turn all those multiplications and divisions into additions and subtractions. Right? So this allows me now to kind of plot everything separately. If I plot the log 20 log instead of the actual function, I can plot everything separately, and because it's all log, this multiplication turns into addition. I can plot everything separately now, and then I can add everything together naturally. So this simplifies finding the resultant plot, makes it a much simpler affair to find the resultant plot. Plus, it makes plotting the curves themselves easier for each of those single constituents. Right? So before we want to continue, I'm going to say that the Bode plot consists of plotting this 20 log magnitude hj omega. Right? This is for the magnitude. With respect, so we do a log on the y-axis, but furthermore we do also a log on the x-axis. This allows us to draw everything as constant lines, as lines with constant slopes. Those are called the asymptotes. We can much more easily draw the asymptotes, which I'll show you how to do that. And then the phase is just the phase of hj omega plotted with respect to log omega. For the phase, we don't need to do the log for the phase. Why? We only do the log for the magnitude, because for the phase, naturally the phases are added and subtracted for complex numbers, right? Here, the phase of this term is going to be naturally added to the phase of this term. When you have two complex numbers multiplied together, the phases add. So it's very similar to the action of the logarithm without having to take a logarithm. So for the phase, we don't have to worry about tagging in a log function, but for the magnitude, to simplify the plotting, we tag in a log function. Okay. So another thing we need to do before we move forward is we want to normalize. What do I mean by normalize? So let me take one pole and one zero. S plus Z1 over S minus P1. So what do I mean by normalization? Well, here, this term on its own, this is j omega minus z1. If I take omega equals 0, this evaluates to minus z1, right? So this evaluates to something at omega equals 0. We would prefer if those poles and zeros, pole and zero expressions evaluate to 1 when omega equals 0. If we set this up, set the poles and zeros up such that they evaluate to 1 when omega equals 0, we call that the normalized form. And this is a form that we prefer because now each one of those expressions can be plotted, can start at unity at omega equals 0, or at the beginning, right? So one thing we could do is we could take the minus z1 out, so this becomes minus z1, right? So this becomes 1 minus s over z1, right? k0, something like that. And then I can take the p1 minus p1 out, so this becomes divided by p1, 1 minus s over p1, right? This is the normalized form. And now this is now a new constant. I can just roll those constants, the z1 and p1, into the k0, and I end up with a new constant. And minus 1 over z1, I just can call 1 plus tau 1 s over 1 plus, call this because it's in the denominator, call it tau a s, right? So this is normalized form because at omega equals 0, this goes to 1, and at omega equals 0, this goes to 1. Any gain is rolled into the k0 constant, right? So okay, so those are the two bases for starting the discussion about Bode plots. We need to normalize the pole and zero representation of the transfer function, and then we are looking for the 20 log, right? So let's rewrite the transfer function in normalized manner. So h of s would be like this. It will be k0, and there's a bunch of zeros and poles, right? In most general manner, not all some of the zeros and the poles could be 0, right? Meaning some of the zeros could be at the origin, could be right. Z1 could be 0, P1 could be 0, P2 could be 0, right? So we could have some expressions, what's called zeros and poles, at the origin, at s equals 0. So this would be Sm. We could have m zeros at s equals 0, right, over Sn. We could have n zeros at n poles at s equals 0, right? And then we have the normalized 0, which is called also a simple 0. So this is a normalized 0, which is also called a simple 0. And then we could have a normalized pole, which is tau a, which is called the simple pole, right? Remember when we said the poles and the zeros, if they are complex, if some of them are complex, they have to come in pairs that are complex conjugate. We can always combine, right? If I have like s, if I have a set of zeros, s minus z, let's say let's say k, and it comes, this is complex, so it must come with a conjugate pair. So though if zk exists, which is complex, then zk conjugate must exist as another 0, right? We can always, multiply this, and we get a second order polynomial when I do that. This becomes s squared plus zk magnitude squared, zk times zk conjugate minus 2 zk. sorry, minus zks minus zks, so it's minus zk plus zk conjugate s. The point is that you get, if you take the complex conjugate zeros or poles and combine them together into one expression, you get what's called a quadratic form, or so you get something like this. So you get 1 plus 2 zeta. Zeta is the damping coefficient. I think we did that when we were working for on second order systems. And then tau 2 s plus tau 2 s squared. So you get this polynomial expression, and then you get one for the complex conjugate poles, or you get 1 plus 2 zeta tau b s plus tau b s squared. This is very similar to what we did for second order systems. We're just taking the second order polynomial and we're defining the constant this way. It turns out that this constant zeta quantifies the damping of the system, how much the system is damped. Tau, by the way, is the time constant. It quantifies how fast or slow the system is, right? And tau typically is 1 over omega naught. Right? So this is called complex conjugate pole, and this is a complex conjugate zero, right? Or this another name for those two expressions is a quadratic pole and a quadratic zero. And that's it. HS might have other terms, but all the other terms will look like this, right? There will be, we've plugged in all the, we expressed all the zeros and poles at the origins. We could have multiple of those simple poles and zeros, and we could have multiple of those complex conjugate poles and zeros. If we know how to do a Bode plot for any of those expressions, single expressions, we can do that easily. We can do it separately for every one of those expressions. If we know how to do that, we can then combine them together to get the resultant graph. So this is a very cool way this is a very cool way of rapidly plotting plotting Bode plots without the aid of a computer, doing frequency response plots without the aid of a computer. Okay, so let's start with all those elements, right? What about those elements? Well, what about the constant k0? How do we plot the constant? Well, we said we were interested in plotting with respect to log omega 20 log hj omega magnitude, right? Assuming we start with a constant. Let's assume hs is just a constant. We said we want to plot all of those separately, figure out how to plot them separately, and then the more complicated hs we can plot by combining everything, right? So let's assume we have the simple case where hs is just a constant. Well, I mean, that's easy. The magnitude is just k. So this is going to be a constant, right? So this is going to be a constant, and the value of this constant is going to be 20 log k0 dB. That's it, right? And what about the phase? The phase is going to be phase hj omega in this case is going to be 0, right? 0 phase with respect to log omega, right? Because the constant has a phase of 0. So this is the Bode plot for a constant. And if we have a complicated Bode plot and then we have a constant, right? So the constant is just a straight line, and we said in Bode plots when we take everything together, we just add everything with each other. So really a constant ultimately, once we have a complicated Bode plot, the constant is just a matter of shifting that Bode plot up or down by that amount. That's what it amounts to at the end. Right? So that's the constant. All right. What about the poles and zeros? So let's start with pole at origin. Okay. So h of s equals 1 over s. That's one pole at the origin. Right? And then we can do a zero at the origin. Well, I mean, this is hj omega is 1 over j omega, right? That's what this is. The magnitude of hj omega is just simply 1 over omega, right? We want to take 20 log, right? What's log 1 over x? That's minus log x, right? That's the basic property of logarithms. So this is x to the minus 1, and I can take the minus 1 out. Right? So this is equal to minus 20 log omega. Right? So yeah, what is the angle of hj omega? Right, so this is 1 over j, which is minus j, which is what? What's j? Is 90, so it's minus 90 degrees. Right, minus j has an angle of minus 90 degrees. Right? So we have all of the information that we need to do a Bode plot. What is the Bode plot? Well, the Bode plot has a magnitude plot, which is 20 log hj omega. And I don't have to keep writing 20 log hj omega. A shortcut for saying that is just saying I'm plotting hj omega in dB. I mean, if I say in dB or in units of dB, if I say here dB, it's understood that this is 20 log hj omega. Right? That's what dB is. dB means this is not hj omega magnitude, it's 20 log hj omega magnitude. So we want to plot this with respect to log omega. So notice the beauty of the thing here. Here, it's just a linear function of log omega, right? It's just what's log omega? Log omega is just, if this is log omega is 0, right? So what's frequency is this? This is 10 to the power 0, right? That's the inverse of the log. So this is a frequency of 1 radian per second, right? But log omega is just this line with slope 1 in this log scale, right? But it has a slope of minus 20, so it's going to be a line that goes down like this, and it has a slope of minus 20, right? But the slope is with respect to log omega, so we say it's minus 20 dB per decade, right? Because every decade, so every decade we go minus 20 dB. So let's say we're here at a frequency like of 10 radians per second. Going one step, so log 10 might be equal to 1, is 1, right? Going one step here in this graph means that we go to 2, right? But what is 2? 2 is log 100, right? So we go from 10 to 100 radians per second. That's the nature of the log plot, of the log axis. So every one step on the x-axis of the Bode plot is equivalent to 1 decade. We're going up 10 times. Going back by 1 unit is equivalent to going back 1/10. So this is equivalent to 1 radians per second. Now, as far as the ticks on the x-axis, you have two options. You can just put in 0, 1, 2, 3, 4. Those are the log omegas. Or you could, by convention, just put in the actual omegas with understanding that this is a log plot. So you could put in 1, 10, 100, 1,000. Those are both acceptable ways of marking your Bode plot. Okay, but the idea now is that the Bode plot for the single pole can be easily plotted as just a straight line, as an asymptotic straight line. Right? And the straight lines are very easy to plot. And the straight line has a slope of minus 20 dB per decade. Okay. Of course, the phase is just a constant, log omega, and then the angle is minus 90 degrees. Okay, so that's a pole at the origin. What if I have multiple poles at the origin? So I have h of s equals 1 over s to the power n. Well, what's that? That's equal to 1 j omega to the power n. Again, I mean, I want to do 20 log hj omega to do the plotty plot. So this is 20 log, what's the magnitude here? The magnitude here of well, see, the thing here is, if you have a complex number, z, and you do zn, what's the magnitude of zn? This is equivalent to the magnitude of z to the power n, right? It has to be the same because the magnitude can be, so this is just the magnitude of z times z times z times z n times. Right? And we said the magnitude could be distributed over if you have two complex numbers multiplied by each other, it's a basic property that the magnitude of the whole thing is equal to the product of the magnitudes of the separate entities in the product, right? So this is equal to magnitude z times magnitude z n times, right? So this is equal to 1 over magnitude j omega, which is omega to the power n. So this is equal minus 20 log omega n. And then we can also take n to the other side. This is going to be minus 20 n log omega. Aha! So now the slope is not minus 20 dB per decade, it's minus 20 n, meaning depending on the amount of poles you have, each extra pole is going to give you an extra slope of minus 20 dB per decade. Okay, and of course the angle, what is the angle? The angle of h j omega right? So we said when we have a product, we just add the angles. So each one of those gives me an angle of minus 90, but I have n of them. So the angle is minus n times 90 degrees. Right? But the phase will remain constant, but it will be shifted 90 degrees for every power of s. And this kind of makes sense, right? Because remember we said that we could add the Bode plots together. So 1 over Sn is equivalent to 1 over S times 1 over Sn times. So just adding straight lines together, we end up with a resultant straight line that has a slope that's equal to minus 20 n dB per decade. Right? And just adding the phases together, so I have minus 90 for each one of those of 1 over S's. So I end up with a phase of minus 90 degrees times n degrees. This is all with respect to log omega. Log omega. Right? So you could think of plotting 1 over Sn as just plotting 1 over S multiple times, n times, and then adding them all together, or we could just derive it directly here, right? It follows both ways. Okay, so now we know how to plot a pole at the origin and multiple poles at the origin. So yeah, okay. So I think I'll continue this next time, and we'll do a couple of examples. All right, thank you guys.